In this video, I'm going to show you how to configure OSPF reference bandwidth. OSPF calculates metric for a path based on the cost of the egress interface, and that cost is based on bandwidth of the interface. So between source and destination, OSPF will add all of the egress costs from source to destination. That will be the path cost. It'll then select the path of the least cost metric based on what's in the routing table. So the default for each OSPF interface is a cost value of 1. Cost is calculated based on the default reference bandwidth of 100 megabits per second. That's the Cisco default. So if you have a fast Ethernet interface such as this one between R1 and switch 2, fast Ethernet is 100 megabits per second. So the reference bandwidth is 100 megabits per second divided by the interface bandwidth. So 100 megabits per second divided by the bandwidth, 100 megabits per second. So that gets you the value of 1. 100 megabits per second divided by 100 megabits per second. Now when you have this link between R1 and R2, that's a gigabit link. That's 1,000 megabits per second. So as a result, you have 100 megabits per second divided by 1,000 megabits per second, and that still gets you the 1 value, since cost can't be any less than 1. And this is the problem. As you have higher bandwidth interfaces, OSPF can't distinguish a gigabit from a fast Ethernet. They're still the same cost 1. The same goes for a 10 gig link. That's 10,000 megabits per second. So 100 megabits per second divided by 10,000 megabits per second still gives you that minimum 1 value. So in this topology here, what I've got is mostly gigabit links, but I've also got this fast Ethernet link between R1 and switch 2. So by increasing the reference bandwidth to 1,000 megabits per second, OSPF will calculate a cost of 10 for that link, since it'll be 1,000 megabits per second divided by 100 megabits per second. And when it comes to the gig links, that'll just be a cost of 1. So it's 1,000 over 1,000. This is important so OSPF can calculate the lowest cost path between source and destination. This server is on 172.16.3 network address. We'll go to R1. There's the route there, 172.16.30/24. So it's administrative distance 110, path cost is 3, that's cost 3, via 192.168.1.2, fast Ethernet 00. That's what it's going to do. It's going to take this path from R1 to switch 2 across this slower link to get to this server. I'll do a trace route. Twice with a packet tracer. So there it is, 192.168.1.2, then 4.2, and then finally the destination. We'll just go to switch 2 here. Fast Ethernet 01, 192.168.1.2. There it is. And so that's the path it's taking. What I'm going to do now is change the reference bandwidth to 1,000 megabits per second, and I have to do it on all devices within the OSPF routing domain. And route OSPF1, this is a global command. I'm going to copy and paste this. You get this message, please ensure reference bandwidth is consistent across all routers. So you want consistency with metric calculation. So I'm on R1 now. I'll just paste that command in there. Then we'll go to R2. An extra hash there. Remove that. It'll cost reference bandwidth 1000. So it's megabits per second. I'll go to switch 2. Finally, DC1. And that should do it. Go back and save this. Make sure it's saved to our next restart. When you change reference bandwidth, you do have to do a clear IP OSPF process, since OSPF has to rebuild the database table and the OSPF routing table. Now sometimes this will work with Packet Tracer. Occasionally you might have to reload the lab, restart it. So if clear IP OSPF process doesn't work, then just reload it and you'll find it'll work fine. Go to switch 1. And just say yes. Okay, so that's all done. I'll just go fast forward about a minute. That's for network convergence. Now we'll go back to R1 and look at the routing table. So here you notice now 172.16.3/24. Now it's via 192.168.2.2 Gig Ethernet 2.0. There it is there. Now to get to 172.16.3, calculating a better path via R2. Gig 000 is 192.168.2.2. Right at the top there. So that's working correctly. I'll just do a trace route. See it there, 192.168.2.2. Then it goes to 3.2 and then 4.2. So gig 01 should be 3.2. There it is there. I'm on switch 2. Gig 01 is 192.168.3.2. That's it there. So it's going up to R2 and then down to switch 2 and then over to the server. 192.168.3.2, then 4.2 and then the server. Now what I'm going to do is shut this interface gig 2.0 on R1, and I'm going to show you the cost from switch 1 via switch 2. Okay, so I've shut this interface, so now packets will go from R1 across to switch 2 over a fast Ethernet link. So there it is there, 172.16.3/24. That's a server network address. 110 administrative distance, and it's got 12 for a path cost via 192.168.1.2 fast Ethernet 00. So it's got a path cost of 12 now. This link between R1 and switch 2, this is now 10, since it's 1000 divided by 100. So FA00, that's the egress, so that's the cost 10 there. Then the egress on switch 2, that's gig 02, that's only cost 1 since it's a gigabit. And then finally this DC1 gig 001, that's the egress to the server, and that's a cost 1 as well since it's gigabit. So that should get a 10, 11, and 12. That's where you get the path cost. Show IP OSPF interface FA00. There's the cost 10 right there. That verifies reference bandwidth is working correctly, and that concludes the video.